trying to explain to students what NMR is, okay? So first of all, let's think about electrons, okay? Where are the electrons? Not in the nucleus, right? They're around the nucleus, but but you guys know about some of the properties of nuclei that might be helpful in understanding NMR. So somebody give me some of the properties of an electron. Charges, negative. What's that? Mass is negligible, very small. Anything else you guys remember about its properties? It's got a funny property about it. What's spin? It's got this thing called spin. You remember electrons have spin? So if anybody ever explains spin to you, I think a simple way to think about spin is we visualize an electron being a sphere and that it spins around its axis, and that creates a magnetic moment. So when we talk about spin, we're actually talking about magnetic moments of subatomic particles. So what's a magnetic moment? Okay, so if I took a bar magnet, it would have a magnetic moment, and its magnetic moment would go from the South Pole to the North Pole. So it's the direction of the magnetic field, essentially, on the bar magnet. So if this is my bar magnet, okay, and again, it's an electron in this case, and it's spinning around, right? And I put it in a magnetic field. Let's say I make the magnetic field go like this. What's the bar magnet going to do? Think about it. I take the way we think about it is you have a bar magnet, and now you put it in a bigger magnetic field. What does the bar magnet tend to do in the larger magnetic field? It wants to line up to it. What do we call that device when we use it, like when we go hiking? It's called a compass. Right? You have a little bar magnet. It's on a pin, and it's aligning to the magnetic field of the Earth. Right? That's the low energy state. Why doesn't it align the other way? Because that's the high energy state. So it wants to go to the lowest possible energy state by lining up with the magnetic field. Okay? So that's a simple way to think about some magnetic behavior. So we think about electrons, and electrons definitely have this behavior, okay? But it turns out other subatomic particles have this behavior. One in particular is the proton. A proton has a magnetic moment. Now, the moments for the proton and the electron are completely different in terms of their size, like a moment being the magnetic field vector, if you guys had physics this week and learned about that this week. The magnetic moment of a proton and electron are very different, but still they behave the same way. So if I take a proton by itself, okay, and put it in a magnetic field, what is it going to do? It'll line up with that magnetic field, right? Now here's the catch. If you have a proton and a neutron, they have spins that cancel out, or magnetic moments that cancel out, so there is no alignment to the field, okay? So things that are often paired up exactly. So think about this now. We're building up nuclei. Hydrogen has a magnetic moment because it only has one proton in its nucleus, right? But deuterium, D2, what's D, or sorry, D, forget D2, but deuterium, the atom, what is deuterium? It's hydrogen with a neutron, right? That doesn't have a magnetic moment. So hydrogen has a magnetic moment, deuterium doesn't. Oxygen, carbon-12 doesn't, but carbon-13 does. And so it turns out you can have a magnetic moment, and generally speaking, it's when you have an odd number of nuclear particles, you end up having a magnetic moment, okay? And that depends on what atom we're looking at. Now, we're going to be looking predominantly at hydrogen, right, H1, and carbon-13. Now, carbon-13 is not carbon-14. Carbon-14 is the one you, well, like, we make jokes about radioactive dating and how we've all been on radioactive dates. But, sorry, I just thought I'd throw that in there in case you never had the joke. It's a different isotope of carbon in terms of natural abundance, okay? Hydrogen is greater than 99%, H1. Carbon-13 is less than 1%. So when we're doing spectroscopy, NMR spectroscopy, we tend to like to talk about hydrogen just because there's a lot more of it. But it turns out if you want to know the structure of a molecule, it's good to know both the NMR spectrum of hydrogen and of carbon, especially in organic chemistry. So we're going to be doing both kinds of spectroscopy. But the principles that you principles that you lose for one, don't lose your principles. The principles that you use for one, you will use for the other, okay? So anyways, that's my little blurb. Okay, so I'm not going to take you through the whole history of NMR spectroscopy. Let's say I have a guitar and it has one string on it, and I start beating it with a hammer. What are you going to hear? Well, first you're going to hear bonk, right? And then what are you going to hear? You'll hear the one string vibrating, all right? So let me freeze this. So I hit this thing with a hammer, it goes boink. I'm not sure if I can spell boink. And then and there'll be a lot of noise, right? And then as that noise dies away, you'll be left with just the string that's vibrating. Why does the string continue to vibrate? Because it has it's called a resonant frequency. It's the same reason you sing in the shower. The shower dimensions, Roger, you sing in the shower, right?
No, I only sing to the pole, not the shower.
I've done it.
Isn't that what causes the resonance?
Yeah, so it creates resonance in the shower. The shower dimensions match the dimensions of some of the wavelengths in your voice. So when you sing, those notes persist over time because they resonate. They go back and forth inside the shower, and you get to hear them longer, and you sound better. Not saying that you sound bad. So if you think about what this looks like on a graph, okay, here's intensity, here's time. It doesn't look like that continuous sine wave. What it looks like is this. This is the hammer. There's some joke about hammer time in here, but that, right? It's hammer time. And then everybody's supposed to go, da, 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 da. Sorry. And then start dancing. So, but what happens is it goes like this. There's a lot of noise here, and then it's going to go like this. Why does it get smaller? Yeah, the energy is slowly absorbed by your body in the shower, right? But slowly the energy is dissipated. That's why we're hearing a sound, and as the energy gets dissipated, eventually it goes to zero. This is known as an FID.
Spiking lines in the beginning.
That's just like the body of the guitar just going, why on earth did you hit me with a hammer? But it's using all that vibrational energy and then translating that energy into the string. But they don't have resonances, but the string does, and it'll carry that sound on.
So it's not like the simple harmonic motion. That's going below and above zero?
Yes. Yeah, supposed to. Yeah. But when you hit it with a hammer, initially you just get a lot of noise. So here's the thing. If you had the right kind of instrumentation, and I'm bypassing a lot of slides by doing all this here. If you had the right instrumentation, first of all, you wouldn't listen to this part here. That's noise. But you would pay attention to this part here. Now we know the amplitude's going down, okay? But if you measure the period of the note, that would tell you what the frequency is. And if you had the right instrument, you can actually take that and graph it as frequency. And amplitude. And what you're going to get, instead of a crazy noisy graph with a bunch of squiggles going up and down, because it's one string and one note, there's only one frequency that you observe. Okay. Now that one thing, if you guys know anything about sine waves, they have a phase and an amplitude. This is actually the magnitude of the phase and the amplitude. Essentially, if you I don't know if they teach this. Well, you guys know what a Laplace transform is? Anybody know what that is? Or a Fourier transform? Kind of hit it in like math, whatever, 8 or 9 or I don't know, 7. End of differential equations, yeah. It's in differential equations. It's a way of just mathematically converting time-based data into frequency-based data. And so we have mathematical, it's like a very fancy log button. Like if you had a button for Fourier transform on your calculator, you could take a series of data points and press Fourier transform, boom, and it'll kick out the frequency components. Okay. What do we call this device that we use all the time? Well, maybe you don't. What is this device that we use all the time that's based on this? Huh? You guys know what an equalizer is? Like in a stereo, an equalizer shows you all the frequency components. How does it get that? It gets that by taking the Fourier transform of your data, and then if you want one component of it louder, you magnify different parts of the frequency spectrum. And so then the highs are higher and the lows are lower, or whatever. So if you play with any of the audio recording stuff in Windows, right, and you record your voice, and you see that weird set of squiggles, right, that comes out of it. You know what I'm talking about, the wave recorder in Windows? You guys know? Yes, no, yeah. You guys need to play more. So, sorry. I told somebody the other day when I was young, we had rocks to play with, and then they invented sticks. So when we got computers, we're like, wow, this is the best thing ever. So yeah, so it's called an equalizer. Anyways, it takes time-based data. That's the sounds you're hearing recorded in real time, converts it to frequency-based data. Essentially, it's doing a Fourier transform on the fly. Okay, so what we're going to do then, just to make this clear, is we're actually going to be taking a molecule, okay, and a molecule is going to be a lot more complicated than a guitar with one string, okay? It's going to be a guitar with many, many strings. In essence, if we're doing hydrogen NMR, one string for every hydrogen on the structure, okay? And we're going to whack it with energy, and the molecule is going to freak out. And then if you wait just about 3 or 4 seconds, now you don't get to hear this, but it could be converted to an audible signal. If you wait 3 or 4 seconds, then what happens is the noise goes away and all the resonant frequencies persist. And they start off high and they go down low and they produce this thing that looks like what I called an FID. This is known as a free induction or free inductive decay. Okay? I don't know. I think it would be molecules that have symmetry because they give one voice in a lot of times, like pure symmetry. They'll have everything, all the atoms will behave the same, so they have one single note that they produce. That might be the coolest thing. I'm not sure you'll hear harmonies and things like that. Okay. Now, so how does this work? Okay, so we have an input of energy, we excite electrons, and then we listen to the resonance energy, and that's what I call the FID. And then we convert that into a frequency spectrum. Actually, you know what I'm going to do? I'm just going to do this. New. It's a lot quicker than writing frequency out every time. So, in order to do this, there has to be 2 energy states. There has to be a low energy state and a high energy state. So we take the molecule, we actually stick it into a magnetic field. Okay, let me show you how we do this real quick. I'm going to grab my props. I put them back yesterday, so I'll lose them. What are you doing? Okay. you guys see this? This is that thing that was in your kit all semester. We haven't used it. I usually introduce it sooner, but we've been too busy. We're going to stick it inside a giant magnet. Now the magnet actually looks like this. It's got a north, it's got a south, okay? And it's got to be connected to be a magnet. So it looks something like that. And then you're going to stick your sample down in here. It's in the middle of this giant instrument. The big white box that's in there, that whole thing surrounds a little magnetic field space that's about this big. And it's to protect it from the environment around it. The sample goes into one of these, and you have to be able to stick this guy exactly inside the magnetic field so that the solution that's in your tube, your sample, like your product or reactant, testing the NMR spectrum, gets in there. So the way we do that is we have this device. Okay. That's to hold it in place. And then we have a gauge. And this sits on the NMR at all times. If it leaves the NMR, it'll break your fingers. No, I won't. But I'll cry. Because this is like the only one of these we have. And it's so nice. And you know how much they charge you for little stupid things like this.
The question I meant to ask you yesterday is whether or not they were clean. Are those reusable?
Yes, they're reusable, and you have to clean them yourself.
Okay.
Yeah, so what you do is, when you're done, whatever solvent you used, if you used the solvent before with the product, you would use it again and rinse it out a couple of times, throw it into the halogenated waste. Okay, we use a lot of solvents, though, that are deuterated. See, everybody laughs when I say that. What does that mean?
Oh, I
Yeah. It has deuterium for the hydrogen. So if you use a solvent that has hydrogen in it, all you're going to see is the hydrogens from the solvent. You'll be like, where are all these gigantic peaks? Where's my product? So we use deuterated solvents so that we don't have to look at the solvent signals. And so we dissolve our product in that. And so it goes into the instrument. This tells us how deep it goes. One of the things that's really difficult about magnetic fields is to have them be really consistent. Okay, so one of the things we do to help maintain consistency of magnetic field or homogenize the magnetic field on the sample is we just spin it at a very high rate. So actually, on the instrument, when you use it today, you're going to drop your sample in there. There's a knob. You're going to turn it, shuts the air off. Sample falls to the bottom. It's just a tube with air coming out of it. And you turn it all the way, and then what will happen is you'll hear the zzz, and it's spinning inside the magnetic field. Okay? So that's to help make the magnetic field homogeneous across the sample. Okay? So, I got to do it from here. Oh, great, I got disconnected. Oh, yeah, sorry. So, let's go back onto this diagram.
And what was FID?
Free induction decay, free inductive decay. It's basically that picture that I showed you, the squiggles going down. Without the first part of the noise going. So we have two spin states, is what we call them, for protons or magnetic moments in a magnetic field. Okay, so the protons, hydrogen atoms, have a magnetic moment. We stick them inside a magnetic field, and it's either going to line up with the magnetic field, like a compass would, okay, or it'll oppose the magnetic field, and this is the high energy state. We never see this in a compass unless you take the compass and you go like this, crazy, and then you look at it, and it'll be like pointing in the wrong direction, and slowly it'll come back to the low energy state. Turns out that's what these guys will do. You start them mostly in the low energy state. You take that energy from the hammer, okay, and the hammer is just an electromagnetic pulse. So if you made it big enough, like you could disable all the electronics in the building, like it's called an EMP, but it's a really small electromagnetic pulse. We pulse the molecule with it. Sorry, I had to bring in that video game terminology, right, because it's in my brain. You pulse the molecules, and then the hydrogens that are at the low energy state will go into the high energy state, and they'll sit there for a while and eventually decay. And when they decay, they produce a frequency of signal that comes out that's going to be proportional in part to the size of the magnetic field. Okay? If the magnetic field is larger, then what happens to the separation between these two? Well, it's harder to turn the magnet opposite of the magnetic field. So that means this energy is going to be higher, and this energy will be lower. Okay? So in a sense, you can say that the magnetic field is going to be, or the difference in energy, I'm going to call this delta. Delta is going to be proportional to the magnetic field strength. The bigger the magnetic field, the bigger the separation in energy. Okay? We don't usually deal with those numbers, but the principle comes into play when you start thinking about different kinds of NMR instruments. Ours is a 90 megahertz NMR. 90 megahertz, if this is the energy, E is equal to h nu. That's the frequency, right? So this energy in our instrument, its native frequency for a proton essentially is 90 megahertz, okay? Our old instrument was a 60 megahertz instrument, okay? It uses a smaller magnetic field because that makes the energy difference here smaller, so then the frequency is going to be smaller, okay? The bigger the magnetic field, right, the better the resolution you have. Because the bigger the magnetic field, the bigger the spacing between the energy states, it's easier to resolve things that are close together. When I went to Europe the last couple of times, we always got to go visit the chemistry departments and got to see their NMRs. And it's generally a thing that people like to do is they like to take you to their NMR room and show you their giant NMRs. And they've got like, they have things up in the, I know, it sounds really bad. But they have instruments that are in the gigahertz range and higher. So I think they're going to, anyways, they're multi-million-dollar instruments. Their magnetic fields are so strong that if you have like a pacemaker, you can't go near them. You can't bring a phone next to them because it'll wipe your phone out. You can't bring credit cards next to them. So the guys who work on these things, you know, they have to take precautions. And one of the things they do, if they really have to take it apart, I guess, is they shut them down. And they're actually, we use fixed magnets. So this is just a fixed north-south magnet, just a very high magnetic field strength. They use superconducting magnets, and they use liquid helium to keep them cool enough so that they can do their high field strength NMR. So high field strength just means a large magnetic field. Okay. So anyways, these are exact numbers. I won't go into this part yet. Okay, so there's this one other thing that affects, okay, so the position, the frequency of the signal depends on the magnetic field, okay, that the proton experiences. What's around the proton? Electrons, right? So if I have a proton, let's say that's my proton, and it's got a magnetic field or electric field around it, who knows what happens when you put a magnetic field through an electric field? Generate a current. It's a circular pattern, so it generates a circular current in the electron cloud. So if I put a magnetic field through, if I put a magnetic field through here, then what ends up happening is the electron cloud begins to rotate, and it turns out what it does is it produces a counter magnetic field. Okay? So think about it like this. Let's say that's the applied field. If our network would keep up, it'd be great. Then what happens is the electron cloud produces a counter magnetic field because it starts to move, and as it moves, it creates a countermagnetic field. This internet is so slow right now. So it produces a countermagnetic field. So the magnetic field experienced by the proton is only from here to here. So the electron cloud acts like a magnetic force field, to put it in cool terms. All right? So you got a nucleus in the middle, shields are on, right? Magnetic field comes through, and it helps to compensate for the amount of magnetic field that it experiences. So it dampens the magnetic field by having that electron cloud. So this comes in to be really important in a little bit. So we know then that the field strength, okay, or the separation energy between the low and high states depends on the magnetic field and on the electrons around the nucleus. Those are the two parameters, okay? The applied field is always the same for an instrument. Ours is at the 90 megahertz, whatever that applied field is, okay? You don't have to calculate it exactly, but that's our instrument. This is on 90 megahertz. Is the electron cloud always the same? No. Okay, let's take a little side trip here, make a whiteboard. So this is an aldehyde, right? How does the electron cloud on these hydrogens compared to the electron clouds on these hydrogens? So we're compare this one, we'll call that A, to B and C, which is going to be these guys. And why is it different? Yeah, it is related to ARIA. Yeah. There's an electronegative atom on that carbon, right? So it's an electron withdrawing group. It pulls electron density away, right? So that's how it's related to ARIO. You have electronegative groups, pulls electron density away. These two, B and C, have lower electron density. Consequently, they experience a larger magnetic field in NMR, which means, in terms of frequencies, they're at higher frequencies. Okay? Frequency and energy are proportional to each other. So in NMR, B and C, these two over here, experience a bigger magnetic field, have a bigger separation in energy between the low spin and the high spin states, and as a consequence are at higher frequencies in NMR. We call that a downfield shift. They're downfield shifted because they're next to an electronegative group. Okay? Does that kind of make sense? You guys follow that reasoning? Size of the magnetic field varies between the hydrogens because of the placement of the electronegative group. If you're close to an electronegative group, you experience what's called a downfield shift. Okay?
So the higher spin is what gives them a higher frequency.
It's not the higher spin, it's the higher separation in the spin state energies. So you have the go with it spin state, and you have the go against it spin state. And that energy between those two gets bigger because the magnetic field changes. Okay? So you can right away, actually, when you're looking at an NMR spectrum and you see peaks that are shifted downfield really far, you know they're against an electronegative group, okay, in proton NMR. So let's look at this a little bit more closely, okay. Let's assume A isn't shifted very far. Compare B and C. Which one shifted further? C is. Why is C shifted further? Lower electron density. Why does it have lower electron density? It's closer to the oxygen, right? So the closer you are to that electron withdrawing group, the further downfield you get shifted. I'll show you examples of this, but it's far more shifted, like 200%, 300% more shifted because it's directly attached. So the closer you are to the electron withdrawing group, the bigger the effect. By the time you're 3 atoms away, it's usually negligible. Okay, other things are more important at that point. Okay, now these are the equations. Just to show you, you almost never have to use them. This is the magnetic field strength, right? The frequency of the signal is going to be proportional to the magnetic field strength. It's also, though, proportional to this term, gamma. This is known as the magnetic susceptibility. I don't put it on the slide anywhere. Let me write that on there. It's not that important, but I'll explain it to you. The magnetic susceptibility, it's just how responsive a nucleus is to a magnetic field. And for hydrogen, it's a lot higher than for carbon. So not only is carbon screwed because it's only 1% carbon-13, but its magnetic susceptibility is also lower than hydrogen's. And as a result, carbon's a lot harder to do. When we do hydrogen NMR, you can deal with solutions that are about 5% product, which means a couple of drops in a couple of mils, right? Or 4 drops in a couple of mils. When you do carbon, it almost has to always be higher than about 80% to get usable data. So it's like, 20 drops of your product, 2 drops of solvent. Why add the solvent at that point? Yeah. Okay. So here's a problem. Magnetic fields are remarkably hard to make consistent. And then if I have a 90 megahertz magnet and you have a 1 terahertz magnet, right, the frequencies where we observe a methyl group will be very different because the frequency depends on the magnetic field. You have a giant magnet, I have a small magnet, not comparable, okay? So the way we do this is we essentially normalize the data. We find a signal that's consistent that everybody can use as a reference point, and then we use that to normalize, that is, put everybody's data on the same scale. The compound for us happens to be TMS. TMS is shown down here. It's tetramethylsilane. Which more electronegative, silicon or carbon? Carbon. So what does that tell you about the electron density around these carbons versus other carbons you might find in NMR spectroscopy? It's higher, right? So those carbon electron densities are higher, so as a result, the hydrogens are upfield shifted. And there are very few things that get shifted upfield in NMR spectroscopy. Most things, because most things are more electronegative than carbon, get shifted downfield. So this TMS ends up being on the far side of our NMR spectrum. So I'll show you what a typical NMR spectrum, the scale, looks like. I'll draw a cartoon out of one, actually. So, let's do this. 0 is on the right. I don't know why we do things like this. How come 0 couldn't have been on the left? It made sense to somebody at one point, right? Typically, it can go as much as like 14 on this side. But that's about as high as you see it. The most so if it goes this way, it's downfield. And then this way is upfield. TMS is set to 0. The unit that we use is known as a part per million. Intensity goes in this direction. And technically, the intensity is a magnitude, so it should always be positive, but it's actually a calculated magnitude. So sometimes, because we're dealing with imaginary numbers in the calculations, which you guys never have to deal with, okay, just saying. Sometimes you end up with a magnitude that's negative because it's part of the, it's got an imaginary component. When you square it and you add it, you can add a negative number. Anyways, it can be below 0, but technically it should always be above 0. That's just the difference between experiment and theory. Okay, so TMS is 0. It's a part per million scale. So let me explain to you how this works. We have a 90 megahertz NMR. That was supposed to be a Z. 90 megahertz NMR. What's that mean? 90 megahertz. 90 million hertz is the native frequency for our instrument. We do everything relative to that native frequency. So if you wanted to know the actual frequencies of like signals, okay, what you would end up doing is, let's say this is at 1 ppm. Or let's do this. Let's call it 2 ppm. What does ppm, parts per million, mean? It's 2 parts for a million, right? So that's 2 over 10 to the 6th, and I multiply that by, I said 90. 90 times 10 to the 6th, okay? The 10 to the 6th cancel, I get 180 hertz. So downfield, when I have a signal that's 2 ppm, it's 180 hertz downfield shifted from TMS. And TMS is set to 0. Okay. Another way to talk about this is as an offset. It's a 2 part per million offset from 0. Because remember, 0 is artificial. We set TMS, it doesn't have 0 hertz as its frequency. Right? We just artificially set it, so it's a 2 part per million offset from TMS. Intensity, by the way, just so you know, 0's down here. And then it goes up. It's an arbitrary scale, in essence, a relative scale. Depends on how much sample. If I put like a 10-fold concentrated sample and a 1-fold concentrated sample, the 10-fold concentrated sample, the signals would be 10 times bigger. So like other spectroscopies, the signal intensity in NMR is proportional to the concentration of the atoms, actually. Just real quickly, the way our NMR works now, it used to be done a little bit differently. We would stick this inside a magnetic field, and we're picking up frequencies from the sample. So the way it works is, draw it on here, is the tube goes in between the magnets, but around those there's a coil. And that is both the radio transmitter coil, the hammer, the pulse, okay, and it's also the radio receiver coil. Because remember, when you hit the sample, right, we don't usually start recording for a couple of seconds because it's too much noise in there from the molecule just basically complaining about you hitting it with a hammer, okay? When it's done complaining, then it resonates. And so what we do is we go from transmit to receive, and on the same coil we use that as a radio receiver. It actually happens in the AM frequency, like the AM band, like 580 and whatever the other stations are. I don't know what they are. That's the only one I know, I guess. Oh, 14 something, and I don't know. Who knows? This is the FID for acetone. Just thought it would be interesting to look at this. All right, here's your intensity plot. Here's time. You notice how this is a very regular period on acetone. That is, the length of the ups and downs is the same. It's decaying because it's resonating and emitting electromagnetic radiation, so it's losing energy. So as it loses energy, it gets smaller, okay? But the frequency is the same. And when you take and you transform this by using a Fourier transform into the frequency domain, so again, this is parts per million is our frequency domain, okay? You have a single peak for acetone. Why do you have a single peak for acetone? What's the structure of acetone? Like this, right? Those methyl groups are exactly the same. Methyl groups, by the way, usually show up around 1 part per million. I'll go over some of these. This one's showing up around 4. What's the deal about the 4 parts per million? What's that?
Well, it's downfilled.
Yeah, it's downfield because the electronegative group, the oxygen, okay? So here's another example. This is synthetic data. I think I stole it from a website. But you can generate these things online, or if you really want to, if you download the license for Marvin Sketch, you can generate NMR spectra so that you can compare, like, oh, yeah, I think that's my structure. What does Marvin Sketch think the NMR should look like? And then on top of that, it tells you which peaks belong to which hydrogens. Okay, so it's very useful in interpreting NMR spectrum. Okay, so this is a tetramethyl pentane. It has 1, 2, 3, 4, 5, 6 methyl groups. Those methyl groups are all the same, so they produce a single signal. Okay, same electron environment, same signal. Yikes! Which of these two signals do you think it is? The one on the right. Why? Because there's more of them. If you look at these two, right, these are 1.2 to 1.4. That's this guy here. It's about 1/9 the signal of this in terms of amplitude, but if you calculate the area, it should be almost exactly 1/9. So remember I said the signal is proportional to how much you have, okay? So you can get the proportions of each type of atom in a structure by doing an NMR spectrum. Then if you know the empirical formula, you can actually calculate how many of each type of hydrogen you have, okay? So if you get the empirical formula, right, and you know it's a 9-to-1 ratio, but then you get that as your empirical, you get the empirical formula for that, or the molecular formula for that, you can use that information to calculate how many of each kind you have. So methyl groups are typically around 0.9. Methylene groups, that's what this is called. I keep saying it, but I'm going to write it on paper here. Methylene. A methylene group is typically from 1.2 to 1.4, okay? So the next thing I want you to get the idea of something, again, I mentioned offsets. There's some offsets that are pretty consistent in NMR spectroscopy. And those are going to come on the next slide. These are some of the typical offsets. If you are attached to the carbon with an oxygen attached to it, your offset's going to be 2.5, okay? If you're attached to, actually this one, a carbon next to a carbonyl, your offset's usually around 1. And I'll show you how you use these numbers in a second. And if you're attached to an oxygen attached to a carbonyl, your offset's usually about 3. Now you notice these two things together would add up to be 3.5, right? So they don't exactly add, because this, right, is a little bit further away. Okay, but those are very common offsets that we see, so it's good to learn like what offset you should expect to see when you're looking at spectra, so you don't get kind of thrown when you see, oh, I don't expect a peak here. Well, you might expect a peak there if you have an oxygen functional group. Chlorines have offsets, bromines have offsets, they all have these different offsets, okay? So it's useful to know what those things are. Okay, so here's the structure. 2-methoxy, 2-propanone. So this is a methyl group, right? Typically around 1.9. But the offset for being next to a carbonyl is about 1. So should be around 1.9, and it ends up being a little bit closer to 2, a little bit bigger than 2. But again, it's in the ballpark of where you expect to find the signal. Okay. This carbon is next to an oxygen this way, next to a carbonyl this way, right? Again, these things don't add up exactly. If you were to calculate it out, a methylene group should be around 1.2. The offset for being next to an oxygen is 2.5. The offset for being next to a carbonyl is 1. 4.7, not so good, 3.5, but it's in that ballpark, right? You know it's going to be shifted far downfield, so you know to expect to find it a lot further downfield than you normally would. This methyl group, right? 0.9 plus 2.5, 3.4, about 3.3, 3.25. So again, you use the offsets to kind of gauge, like how close is it to that electronegative group that's in my formula? So you can imagine how you would use this with IR spectroscopy. Right? IR is going to tell you, oh, I've got an oxygen, but it'll tell you if it's an alcohol or if it's an ether. Right? If you have 2 oxygens, it'll tell you if it's ketones or if it'll tell you if it's carboxylic acids or esters. And then you would use that information along with your NMR information to put the structure together. Okay? It's like doing puzzles. And the way I actually teach it is to do Post-it notes. So when we do it in lab, I'll give you a stack of Post-it notes, and you get a formula. You draw functional groups on Post-it notes, and then you just start moving stuff around until it fits. Okay.
Is there any real reason the methyl next to the ester is higher than the methyl next to the carbonyl?
Methyl, it's not an ester, but because it's further away.
Ether.
Yeah. So this one here is further because the offset for being attached directly to the oxygen is 2.5. Is that what you're asking?
Well, just because it's high, the intensity is higher.
Oh, yeah. So how many hydrogens are here?
Well, that one's 2.
And this one is?
That one's 3. But then on the other one, it's 3, but it's lower.
Yeah, but the amplitude is misleading. It's the area, because what happens is it's like in IR spectroscopy, how peaks can get broad or narrow from hydrogen bonding. So depending on the structure, peaks can be a little bit broader. And these things are so narrow to start with, you make it a little bit broader, the amplitude drops way down. So actually what we do, okay, so I'm going to tell you how we used to do it. Well, I don't know if I tell you exactly how we used to do it, but it used, the computer that would do this was actually an analog electrical circuit, and it would essentially calculate the area under this peak by integrating trapezoids. A trapezoid rule? Got a point, get an area. Got a point, get an area. I kind of lied there. It actually used a what's called an integrating electrical circuit. If you guys don't know what that is, that's okay. The very first digital versions literally did trapezoid rule, and they would plot a line. This is 0, it's flat, and then this is an increase in the area. That's calculated by calculating trapezoids and scaling it to the screen dimensions, basically. So this jump from here to here is for 2 protons. This jump from here to here is actually 3 protons. This is 3 halves bigger than that. This one and this one are almost exactly the same because they're both for 3 protons. So the ratio would be 2 to 3 to 3.
So the spike above doesn't actually matter. It's the line across.
It's the line across. Now, okay, so better yet, in new instruments, they just put a number down here. And you can set, for example, when you do it, you might initially set this 1 to 1 because you don't know how many hydrogens there are. So this will be 1, this will be 1.5, sorry, yeah, and this will be 1.5. And then you'll say, oh, I can't have a half. So I'll multiply that by 2, and you can put a 2 in here, right? And this will become a 3 and a 3, and you'll get these numbers out. But they literally just give you the numbers, and they scale them to whatever value you want to. Oh, okay, good. We're working again. So this is a little bit about the integration. I was going to come to it on the next slide, but skip that for now. Skip that for now. Last thing that I want to talk about. Oh, I'm out of time. Shoots. Okay, I'll continue this lecture in lab. I'm going to take a break.